Hello everyone. Today we will talk about how to reconstruct binary tree from traversal data. Given an in-order traversal sequence and a pre-order traversal sequence of a binary tree, write a program to reconstruct the tree. Assume each node has a unique key. For example, given an in-order sequence of F, B, A, E, H, C, D, I, G, and pre-order sequence of H, B, F, E, A, C, D, G, I, we can reconstruct the binary tree as the graph on the right. The problem seems a little bit hard at first glance. Let's first review the basic knowledge about in-order traversal and pre-order traversal. For in-order traversal, the rule of thumb is to memorize the order of traversing. First print out all nodes in the left tree, then root, then all nodes in the right tree. Take the previous graph as an example. At first step, we need to traverse all nodes for H's left tree, noted as H's left child, then H itself, then H's right tree, noted as H's right child. At second step, we take a closer look at H's left subtree and find its root is B. We need to print all nodes in B's left tree, then B, then B's right tree. The next step, B's left tree, is just F, so put F on the sequence. As for B's right tree, E doesn't have a right tree, so add A and E to the sequence. Now we have finished all nodes on H's left tree, which are F, B, A, E in sequence. We apply the same procedure for H's right tree and finally get the overall in-order traversal as F, B, A, E, H, C, D, I, G. Pre-order traversal is similar to in-order, but we need to put root at first, then left tree, then right tree. Given the same graph, we put H as the first node because H is the root, then H's left tree, and H's right tree. For the next step, we take a closer look at H's left tree. The root of subtree is B, put B on the list, then B's left tree, which is F, then B's right tree. As for B's right tree, the root is E, so put E on the sequence, followed by A. The same thing happens on H's right tree. We put C on the list. Since C has no left tree, focus on C's right tree, whose root is D. Put D on the sequence, followed by G and I. The brute force method is easy to think of. We can enumerate all the binary trees based on in-order traversal sequence, then verify each of them by applying pre-order traversal. Please note the verification needs O of n time, and also there are many possible cases. The final time complexity can be huge. We need a few insights to solve this program properly. We know that pre-order will always put root node at first. By checking the first element of pre-order, we know the root of the whole binary tree. Then we can find its corresponding index in in-order traversal. Then we can know what nodes are on the left tree, and the rest will be on the right tree. The first element of pre-order is H. By checking its entry in in-order sequence, we find F, B, A, E are on the left tree, noted as blue, and C, D, I, G are on the right tree, noted as green. Then we can also mark these nodes in pre-order sequence. There are 9 nodes in sequence and H is at position 5, which means there are 4 nodes in the left tree and 4 nodes in the right tree. So in pre-order sequence, the next 4 nodes following H are in the left tree, then the next 4 nodes are in the right tree. As we have new pre-order and in-order traversal for each subtree, we can repeat recursively to reconstruct the binary tree. Let's go over the example. After we determine H as the root for the binary tree, we can construct in-order and pre-order sequence and recursively call on the left subtree and right subtree. Look at H's left tree. By checking the pre-order sequence, the root is B. Its position in in-order sequence is 2, so we know F is in the left subtree and A, E will be in the right subtree. As for H's right tree, the root node is C. C is the first element in in-order traversal, which means there is no left tree under C, and all the other nodes are in the right subtree. Put F directly under B's left tree because there is only one element in the sequence. As for B's right tree, we find E is the root, and A will be E's left tree. Use the same procedure for C's right tree, where D is the root, and G and I will be in D's right subtree. By checking the pre-order sequence, we find G will be the root, and I will be G's left tree. This is the overall demonstration for applying the algorithm on the example. Feel free to pause here and go over all the recursive calls. Please make sure you understand all the procedures. There is one more question we need to think of. Given the root node, such as H, how do we find its index in in-order traversal sequence? We can do a linear search and stop as soon as we find H, but each search will be linear, and during recursive calls, we need to find such index for all nodes. This will make time complexity n square. We can use some extra space to save time. Build a hash table to record each element's index. The key will be node and the value will be index. So given a node, we can look up its position in constant time. The above algorithm will be in linear time complexity because we only access each element once. The space complexity is made up of two things, hash table and function call stack. Hash table will have O of n complexity, and in the worst case, function call stack will also be O of n. Here is the actual implementation. In this part, we will build a hash table to record each element's index, then call the helper function to return a whole binary tree. This is the recursive function. It takes in the pre-order sequence, the start and end markers to indicate the range we are dealing with for both in-order and pre-order sequence, and also the hash map. Please note, we need to define the base case for recursive calls. In this implementation, if the range we are dealing with is invalid, we return a null. As we know from previous demonstrations, a leaf node will have only one entry in pre-order and in-order sequence. Its recursive call should have an invalid range on the left tree and the right tree, so we can set both to null to mark it as a leaf node. This is the recursive call for the left tree. Please note that it set the pre-order end marker based on the size of the left subtree and used the first half of in-order traverse as range. This is the recursive call for the right tree. You can try out some variants of this problem to see if you fully understand this algorithm. Instead of given in-order and pre-order, given in-order and post-order, try to reconstruct the binary tree. How about given pre-order and post-order traversal sequence? That's all for binary tree reconstruction. Thanks for watching.